First of all, I thank you for the kind invitation you have extended me to, interact with the students here. It's a great opportunity for me. And at the same time, you have taken a lot of, kind of thing to invite me also. I am really indebted to you, sir.
Don't say that, sir. Don't say that, sir. We are happy to see you here in our college.
And other people like Vyas as well as Madam, they are all, taking a lot of interest to see that kind of come here. I thank all of you. And it's an elaborated introduction you gave me. It was, not necessary that much. You would have given my education where I got it. That would have been thank you. So, I take it that you're all master students and a few faculty are there as well. So I'll be speaking on two things. One is about the luminescence, the technique, and then another one is HPLC technique. When I looked into the schedule what you have, there are so many people speaking about HPLC. So I will speak that at the end. I made it in a very simplistic way of, explaining HPLC. First I will discuss about the luminescence. So how much time I have, madam?
It's yours, sir. All day is yours.
Okay. Now it is almost 11:45. So I will take one lecture up to 1 o'clock, sir.
Then we break for lunch and then come back.
Thank you, sir. So I will take the luminescence. So I thank my institute, IICT. If you can switch off this light, madam, then it becomes easy for that. It's okay now? I think it should be visible. This one?
It's okay. Is that okay, sir?
Fine. If it is fine with you, no problem.
Can everybody say? Yes. Yes.
I think it is still not 12 o'clock. So, good morning to you all. Excellent. Good. Now we start. Right? So, what I will be speaking to you is about the luminescence. This is one of the techniques which use it, to come extensively. I will take it to the real-time application. There you will have, fantastic appreciation. So, next slide. Yeah, he is actually the Georges Hammond. He visited Indian Institute of Science, Bangalore, and then he says that making chemicals is not a big thing. Finding out the properties are most important. Who will find out the properties? Pharmacy people. Okay? Organic chemist, me, I can make all kinds of chemicals. Every day I go to the lab, mix A, B chemicals and get a new chemical C and D. I am excited. I am thrilled. But what is the use of that chemical? You speak about pharmaceutical importance of that chemical. So he is most relevant in an indirect way. He visited us. He was, big man there in USA. He is the, person who is responsible for making the photochemistry as one of the, field of the interest. This is around 1980, which, in this you can find out where I am here. That's how I know. Big difference. Next slide. Yeah, this is our research interest, what we are doing at IICT. This is organic photochemistry. That's the interaction of light with organic molecules, where the pharmacy students will be doing it regularly. If you are really analytical, pharma analytical, you look into the photostability of each and every drug what you come across. So this is an important thing for you. Organic materials, which synthesis of heterocycles and bioevaluation, most of the drugs what you get in the market now, they are all heterocycles. Invariably, over 80 to 90% are heterocycle. So we thought that we should learn and then understand what is heterocycle synthesis and then bioevaluation. Method development API, this is the most important for you people, where I was able to train over 100 students. దగ్గర పెట్టుకుంటారా అంటే నా గొంతు పెద్దగా ఉంది కనుక గట్టిగా అవుతుందని చెప్పి రీసౌండ్ అవుతుందని చెప్పి నేను వెనక్కి అవుతున్నాను అంతే. Is that okay with you? Audible? If you have any problem, you please tell me. Okay? So the fourth one, which is method development of APIs, active pharma ingredients. That's the most important thing for you. Okay? So we started doing that for the past almost 15-20 years, where young pharmacy students particularly, they come to me and start working on developing a method for the, drugs available or the formulation, drug formulations which you take it in the form of tablet or syrup or a capsule or whatever kind of thing available in the market. So analyze them, and then this is what way we started. To initiate this, I must thank another professor here. His name is Professor V.Jayathirtha Rao Emeritus, who is from Andhra University, Visakhapatnam. He is a pharmacy analytical. So we never met for about 12 years, but we started working together over email and then later, telephone correspondence. So we never met. After 12 years we met, after 12 years of association. So I used to get students from him. If he recommends, I will just take his student. Now I don't see here and there. His signature is valid. That's it. That's how it goes. So it went very well, and then part of the story also I will tell you. So that's how we got introduced into method development. The trick what I played here is, I used to send the pharmacy student to the nearby industries in Hyderabad. So the guy will go there and then get into the formulation unit and then catch some drug or the pharmaceutical what they are formulating it, and he comes with a gram of that material. And then we start working on HPLC and develop method and validate it and then look at the stability studies, all kinds of things we do it. After completing it, he is a hot cake for the industry because he has already worked on the product without any effort from the industry. So he will be immediately absorbed in that formulation unit without any. That's how it linked very well and program went very well. Still it is going on now. I am Emeritus Scientist. I still have a couple of students to work it, and then I am winding up. So next. Luminescence is the technique which you come across. So what is luminescence? It is an emission of light by any substance. Any chemical material or any material you take it, if it emits light, then you call it luminescence. Okay? And the luminescence does not result from heat or light due to, light due to heat is called incandescence. Okay? You have a bulb at home, old people, old, tungsten lamp, where you send the electricity to that, the tungsten filament gets heated up and then emits light. That's called incandescence. Cold body radiation, these are a few things which you do. Next slide. Types of luminescence. Probably you might be interested in knowing it. How many types of luminescence you get. So chemiluminescence. Chemiluminescence, it is when you mix chemicals, it gives light. So that is called chemiluminescence. Here you are making use of the chemical energy, converting that into light energy. So a chemical energy is getting converted into light energy, so you call it a chemiluminescence. That's how it goes. Okay. I will show you. An example is also there. Forensic science, people. And then in the CID also, if you watch Sony CID, night time, you can get that. I will give you that example. Bioluminescence. In bioluminescence means the light is produced in a living system. You can see that, firefly, which you see it in somewhere during the rainy season. Evening times you will have a milugu purugu we call it. So that is also. So it is light is generated through a biological system or a living system. You call it a bioluminescence. That is it. So you do have fungi and then squid and jellyfish. So many is there. The jellyfish got Nobel Prize. Honestly, I have one slide I will show you later. So bioluminescence is very, very important to understand why a given system or a biological system should produce that light. So that's why should it go? Why nature go for it? That's most interesting. Next slide. This is triboluminescence. If you take some quartz crystals and rub it, you get a light, right? Very simple experiment I will tell you. You take, you have sugar, chakra ఉంటుంది కదండి, డబ్బాలో చక్కెర ఉంటుంది, చక్కెర చేసేసుకొని మీ దగ్గర అది రోలింగ్ పిన్ ఉంటుంది కదా, చపాతీలు చేసేటువంటి ఉంటుంది కదా, దాన్ని పెట్టి గట్టిగా తిప్పేసేయండి. తిప్పేసి మీరు ఏం చేయాలంటే లైట్లని ఆఫ్ చేసేయాలి కిచెన్లో. ఇది చేసేసి చూస్తే యూ విల్ గెట్ ఎ బ్లూ లైట్, faint blue sparkles you will get it. So this is called tricholuminescence. So light from a substance caused by rubbing, scratching or similar frictional contact due to breaking of chemical bonds, that will give you the energy. That energy is converted into light energy and get it. Sonoluminescence. You can see this is, sonoluminescence is, converting sound energy into light energy. Novel sonar waves, sound waves traveling through water could create a bluish glow. That's why you see the sea, it will be in a faint blue color kind of thing. And then when you draw a sea kind of thing, you invariably give us blue color to that. Why? Because it shows the blue color. The blue color is due to sonoluminescence. The waves, the sound waves get mixed up and converted into light. Next slide. Electroluminescence, of course, we enjoy this. This entire room is filled up with all these lights. Just now this gentleman switched off the light. What you are doing there? You are passing electricity and taking the light. Okay? This is most important. So the problems what we have with the present whatever lighting system, the efficiency is less than 10%. That means 90% of the electricity is going waste. The LEDs, recent lamps, I think it is some of these things are with LEDs, I think. Okay? All of them are LED. So why we have gone for LEDs? Because efficiency has gone up. You don't have to spend that many units what you are spending earlier using our incandescent bulbs or the tube lights or other Excel kind of a lamp. So here it is reduced. So this efficiency is coming. Next generation is OLEDs will be coming. Organic light emitting devices, diodes, that will be still cheaper and then better also for home lighting. These things, you have a very highly penetrating radiation coming out of these lamps. It hurts your eye if you look at like this. Whereas the organic light emitting diodes or devices, it will be very soft. So you compare, sunlight versus moonlight. So moonlight is pleasant, enjoyable, whereas sunlight is highly penetrating. That is the difference. So it will be coming up slowly. Yeah, this is what plasma TV, what we have it, and then exit, all kinds of things you can do it. And then radioluminescence, of course, you are familiar with it. Radioactive material, you put it in your watch, clock, all kinds of things. So that gives you light. And then, that is called radioluminescence. Next slide. Thermoluminescence. So this is another thing. Emission as already excited molecule can in some cases be enhanced by application of heat. This is known as thermoluminescence, that is distinct from the black body radiation. That with some minerals and above all with crystal phosphors after they have been excited by light. See, what is happening is you take that rock, whatever, phosphor kind of thing, and you shine light on it. So light is being absorbed already. When you heat that kind of a status of the material, it emits light. So it is thermally activated and then thermally given. So that's called thermoluminescence. And in photoluminescence, which we do it regularly at our labs, photoluminescence. You given a chemical and then it gives you light. That's called photoluminescence. The luminescence is initiated by light. That's called photoluminescence. That is two different types of it. Can I have this one? Yeah. Here you have a fluorescence and phosphorescence. Fluorescence, you have all these properties. Okay, singlet excited state. Lower energy than the absorption, and then typically it takes place in a nanosecond time scale, whereas this is at millisecond, microsecond to millisecond. Lower energy than the absorption, definitely. Emission from the triplet. These are the two differences. So when where you get all these kind of application, you can get some applications. Many things, the paints they put it all over. On the police people, they wear some kind of a cross kind of thing, and the men at work, when they wear all these kind of phosphors. So when you shine light on it, that emits light. So you do have some applications there. And then you have medical applications, I will tell you later. Next slide. What I will be speaking to you is about principles of little bit of fluorescence and little bit of instrumentation, and mostly I will be concentrating on applications, which will be interesting to you. Next slide. Yeah, this is the standard thing which we do it. It's called a Jablonski diagram. So what it represents is You have some lines here some lines, and here some lines. Each thing is called a ground state here, and this is S1, first excited and second excited state. So that's what it is represented. And then it is many a times it's called a state energy level diagram. These are the states involved, singlet, triplet, S1, S2, and then energy. We talk about their energy. That's why it's called state energy level. And then level means the different levels they are placed. You can call it also. So you can take this data. I don't know whether you are familiar with this kind of thing, but it's a standard thing which you require to know it. So when you excite when you shine light on a molecule which is in the ground state always, it goes into the singlet or the second singlet, and then it can emit light. We call it a fluorescence, okay? Or it can come down to the S1 level, and then it undergo inter-system crossing to triplet, okay? And then a triplet can give you luminescence. That is called, we call it a phosphorescence. Okay? The time scales are given here. These are the several, terminology involved in it. This is the most important and fundamental thing which you should know it. That's what I thought I can show it to you. And yeah, next slide. This is also another way of representing the same thing what I gave it to you in the jablonski diagram. So here it is. It goes like that: excited state, emits light, heat, and then photon, and then different way. So here are some of the things which I have done. Suppose a molecule is illuminated with the light at a resonance frequency, right? Light is absorbed, and then you use B-Lambert's law. That you apply how much light. This you will be using it regularly in your studies. Even B-Pharmacy students also, they use this equation to find out quantification of several drugs and other things by UV visible spectrophotometry. Excitation following light absorption, a chromophore excited some higher electronic energy level, S1 and S2. The absorption process takes place on a time scale of 10 to the power minus 18 seconds, even less than that. We do not know because we could not determine how much time a molecule takes. That still is a debatable point. Many people are working, whole world is working to understand that. That is a very, very interesting and philosophical, let me tell you. The light energy is converted into something else. Okay? That is the interface. Energy conversion is the interface. Understanding that is a real thing, That's why it is taking a lot of time, or we are unable to find out how much time it takes. Although we see it, even our eye also takes light, but we don't know how much time it takes to absorb a photon. It is less than 10 to the power minus 18 seconds, because the laser what we have presently available in the world is attosecond laser. Okay, that laser unable to determine this number. That's why we say it is less than whatever 10 to the power minus 18 seconds. That's how we say. If someone invents it or discovers that will be a great discovery, definitely. Next slide. This also we call it a potential energy curves. A different form of mentioning them. Instead of lines which I show you, here it is a potential energy curves we can show you. Next slide. Yeah, this is the shape of the emission spectrum. When you record luminescence or phosphorescence or fluorescence spectrum, this is how it looks like. So if you take anthracene, if you put a line in between these, you have exactly a mirror image relationship. That is possible. Or it may not have a mirror image relationship also. Both the ways is possible. Okay. So this is this gives you this will be the intensity, this one, and this will be the wave number or wavelength, whatever you want to call it here. Photon energy in electron volts also they mention it. That is also there. Wavelength, nanometers also you can see. 300, 350, 400, 600 after that. This is absorption and this is the emission. They are not mirror image. So these things shows different energy levels involved. Probably vibrational energy levels are also involved. In this case, it is the different vibrational levels of anthracene, the C double bond C. That's how it is being interpreted. It's a simple interpretation. You need more experience to take these things and interpret it. That comes by experience. Next slide. Yeah. So whenever you want to do a luminescence technique to be used, you require to select a proper concentration range. That is most important. If you select some different concentration range, you will not get reproducible results. So you have to select a concentration range only here to here, then you will get a reproducible result. Because you do have several, parameters involved in it, interacting and then deviations, all kinds of things are there. So this is the tricky thing here. But higher concentration, the linearity may be, deviates significantly. That is what it is given. So you have to be careful in that. Next slide. So advantages of luminescence spectroscopy. First thing is over 1000 times more sensitive than UV visible absorption. That is the biggest advantage what you have it. Once you say 1000 times, you can determine whatever limit of detection, limit of quantification at a level of nano, even less than that pico also you can go. Picogram level you can go in. There's absolutely no problem. Because of 1000 times more sensitive than UV visible absorption. That is the biggest advantage you have. And then it is much better than your radioactive technique. Radioactive technique, you do have a problem of hazard, health hazard. That radioactive light lays, it hits your body, you have a problem in a long run. You cannot work on it. So it is limited. You can use it but limited. But whereas this one, it is more sensitive than your radioactive technique. That is also another advantage what you have. Only thing, the molecule should be luminescent. It should show some fluorescence or phosphorescence or any kind of thing. Okay? Luminescent will show. That is the only criteria. Non-invasive method, you are not losing any, chemical in that. There is no loss in it. You can recover back after your studies. Real-time measurements are possible, especially useful for medical purposes. This is the most important. I do have quite a few slides where luminescence technique is being applied for the medical and day-to-day assays, day-to-day what you call it, when you are not well, you go to a doctor and show them, he will be using the luminescence assay. How he is using, I will show you afterward. So this is about the, instrumentation. This is the kind of a luminescence spectrometer what we have. Probably Agilent, person who is here can also show it. We have purchased one Agilent, luminescence spectrometer also. It's also similar, but this is much bigger than that. This is, Parivazo in Yuan. So this is the light source. This one, where you do have a 450 watt xenon arc lamp, which we use xenon arc lamp, very high intensity lamp. 450 watts, okay? And when they switch it on, the light from this compartment enters into this compartment, which you call it as a excitation monochromator, okay? So this box contains gratings where you can tune the wavelength, whatever wavelength of excitation, with plus or minus 0.1 nanometer accuracy you can do it. So nowadays we do have a fantastic grating technology developed, so that you can tune up to that level also. So what we have a double monochromator. That means 2 times we have put gratings. That means you really resolve that excitation wavelength to a very accurate value. That's what we did. You can buy a single monochromator also, single grating, but we purchased it. And this blue color box, where you keep your sample cell, like UV cell, UV visible spectrophotometer, same cell you will be putting it and then observing the luminescence. So luminescence, what we observe is, if you are passing light to your sample in this direction, 90 degrees to this, we will observe the luminescence. That the light coming from the 90 degrees angle of your cell will be put into a detector. Okay? So the detector invariably will be a photo multiplier tube, which catches photons and then amplifies and gives you the signal. And you do have it nowadays, computers we have it, software we have it, we can do it and then it's a very simple. And then if you run the fluorescence spectrum for about 10 to 12 times, you will understand complete and you will become easily you can graduate as operator level, you can easily pass it. But interpretation is another thing, it requires a little bit more knowledge to work on it. You have to read various books and then journals and other applications. For that you need more, and then constant urge is required in that. So this is also another simple diagram which is mentioned here. This shows that light is emitted in all directions. That is the problem we have it. So if you put whatever cuvette in that and then shine light on it, the light will be coming 360 degrees. Everywhere it will be emitted. He cannot control that. So you cannot make the molecule to emit in only one direction. No, not possible. So that is the limitation what we have. So for that what we do is, we take a standard and then compare with that always. Next slide. Yeah. These are the few things which we come across as a luminescence, fluorophores you call it. You can say fluorescence, or then molecules that show fluorescence called fluorophores. Okay. Requirement for a good fluorophore: aromatic ring, extended pi conjugation, at least one electron donating. These are the thumb rules which we use it. The fluorescence, which we use it every day almost, red color kind of thing. It has an application also. I will show you that slide. So the structural changes what it happens. So in this form it doesn't fluoresce. When this ring opens up, lactone ring, and then it emits light. That is the chemistry. You always look into the chemistry also, because I am a chemist, so I look into the structure. The structure responsible for the emission which we look. So this is the structure responsible for the emission. And then you require some kind of a hydroxy group, amino groups, all kinds of things. You might have heard about rose bengal and other chemicals also. Okay. So what you can do is, further the chemists have given this kind of a thiocyanate linkage they have put it. So this kind of an active whatever site it has, it makes a covalent bond with hydroxy or amino or other groups also, which forms a covalent linkage, and then you can derivatize this fluorescence with various drugs and other things where you have an important, and make them luminescent. That is the advantage you have it. That's why they have linked this thing. That is the chemistry part of it. Can I have next slide? So in biological systems, you do have several molecules showing luminescence. What are they? I just listed here: tryptophan, tyrosine, phenylalanine. These are the amino acids. They show the fluorescence in this region. That means if you have these residues in your protein or enzyme, you can use that enzyme or protein for the natural fluorescence. Okay, inherently. And then you do have structural proteins, collagen and elastin, of course. These proteins also part of this amino acid, which is building block, so they should also show the fluorescence. And enzymes like FAD, NADH, NADPH, they also show the fluorescence. These are the prosthetic groups or coenzymes, whatever you want to call it. Vitamins like vitamin A, K, D, all these vitamins, they do show fluorescence. And then B6 compounds, you do have several. Okay, B12 also. Pyridine association. Lipids, sometimes they show it with conjugate with something else. Or firings, they show the luminescence. That means you do have several molecules of interest in biology. They do show the fluorescence. That means you can make use of this fluorescence technique for studying various kinds of things. Can I have next slide? These are the few things which I told you. This is called ethidium bromide, which complexes with the DNA very, very strongly, and then you can study the the DNA structure and other kinds of things which using this ethidium bromide. And these are the acridines, diaminoacridine and then methoxychloroacridine derivatives. This is called dancyl chloride. This is also very highly fluorescent. So you can attach this to many drugs and other things, makes it fluorescent, and study them. Why you should study? Because of this sensitivity. You can measure at a picogram level also. You can determine limit of quantification, limit of detection will be at higher level. That is the advantage you have it. Next slide. There is one more thing which comes: fluorescence lifetimes also. So these are talked about in nanoseconds time. Time tau 1 is the one of the excited state having this 0.54 nanoseconds. And then second excited state which is having 4.45 nanoseconds lifetime. That means it takes that much of time to emit light. After absorbing the light, within that time limit, it will be emitting the light. That is what. FAD, you have 2.63 nanoseconds and 0.36. This is a very interesting thing. George Porter, who got the Nobel Prize for this, he was the first person to analyze these, lifetimes and other. He is a physical chemist or a photophysics knowledge. So he did that thing. After that, he invented nanosecond, and then picosecond has come, femtosecond also got Nobel Prize. He is a Egyptian, American who got the Nobel Prize for that, femtosecond laser. So you can determine the lifetime in picosecond, nanosecond, picosecond and femtosecond time intervals also. Why you need? You would like to know the stability of that, how long it stays after absorbing. These are the few things where the physicists will have more interest. Next slide. You do have temperature effect, solvent effect, lower temperature increases. When you cool the system, it emits more light, because by cooling any system, it loses its translational motion. So the collisions will be reduced. When you cool the system, the molecules will not move that fast. So you arrest the translational motion, and then you arrest their rotations, and then other wagging type of thing. Those you arrest all those freedom. When you arrest this freedom, then the molecule will bound to emit light. That's how it goes. Solvent also, heavy atoms will decrease the fluorescence, and then heavy atoms like mercury or bromine or iodine, they reduce the fluorescence. May emit more in polar solvent and non-polar. This is, you need more experience when you deal with the technique. You will understand this. Then it comes by experience. Next slide. This is how the energy level diagram is shown. When you put it in a temperature, it goes into some intersystem crossing, gets into the phosphorescence, and then that may not emit light. The triplet light, triplet do not emit light. That's what it's shown. Next slide. Yeah, this is also again, you do have a ground level elevated and then decrease in the excited. There's so many diagrams, cartoons you can show to understand this mechanism of interaction of solvent. Next slide. Solvent, it is the same thing, how the dipoles are oriented. That is what it is shown in the excited state in this. When they orient like this, then you have a lowering of energy level, and then the emission wavelength will be longer. So we all did, we published papers also using the small molecule. So that also. Switch off that. I forgot. I'm sorry. So dipoles, you can show them in this orientation, which affects the energy level, and you will have a longer wave. We did a lot of studies also. We explained it. Next slide. These are the few heterocycles which we come across: indole, isoquinoline, quinoline. Aromatic contains whatever carbonyl heteros, more likely to show phosphorescence. Phosphorescence little less introduced. Intersystem. These are the few principles which we looked into that, and then we say that even heterocycles also can do it. In fact, we were able to make variety of heterocycles for the application of organic light emitting diodes, where we were able to see higher fluorescence. Next slide. Yeah. This is another charge transfer process also. We can see it. We call it a charge transfer state, or twisted intramolecular charge transfer, TICT. There's some new terminology comes into picture, and then we do it. So this is another thing, stands for dual fluorescence. Okay. This is one state showing and another showing. So this is the S2 and this is the S1. Both the states are showing the fluorescence. Next slide. Yeah. Excimers and exciplexes. This is also another new terminology which is involved. Excimers mean you have one excited state, another ground state. When they interact, you call it an excimer, singlet excimer. Okay? And then exciplex mean you have A and B molecule, either A in the excited state or B in the excited state, which interacts with either ground state A or ground state B, which forms a complex and which emits light. You call it an exciplex. These are the few terminology involved in it. So those also can contribute to the luminescence. We have observed all these things in our lab. which our students are working. These are all most important when you use it for LED bulbs which you are using. They are most important in that. Structure is being collapsed and you do have a shift in the emission wavelength to longer wavelength. Okay, so all these things shows that there is something is happening to the molecule in the excited state. That is what we had to infer. What is that happening? It will be difficult to get the structure of the excited molecule because the short lifetime it has. But we can predict it always. We can guess it always. People are working, but we don't have answer for that also. Next slide. Yeah, this is about the 5D, which has a fine structure which collapses into broad emission. Right. Next slide. This is the naphthalene. All these things. We have published all these things. So this becomes a broad structure. Structureless broad emission it becomes. So these are the few inferences which we wrote down, and then we say that fluorescence lifetime, quantum yield, polarity, all these things will contribute to the nature of the excited state, which we can find out and say it is more polar. Next slide. I'm sure you will be interested in this real-time applications. So we have a problem. What problem we have? We are taking water every day, drinking water. We don't know what are the ions involved in it. That is mercury or fluoride or chromium. There certain things are very dangerous. Chromium, you get it from the leather industry. And then fluoride, you have a problem in Nalgonda district where the people have a lot of fluoride in the water. When they drink that water, their bones will get twisted and it becomes, they become physically disabled. That is the problem they have. We have seen that. So you require a method to analyze these fluoride or chromium, all kinds of ions which present in the water. So for pharmacy people also it is very important. Whenever you use this kind of a water, you must tell what are the contents of the water, why you are using it for purpose. And then if you are formulating something, syrups or kind of a viscous liquid, all kind of thing, you have to tell that thing. So for that, you have to analyze the presence of cations or anions. So we started looking into that. The new method you can develop and say, so this is the purpose of it. Hence, development of new methods to monitor the metal ions present in the drinking water sample is extremely useful, essential actually. It is not extremely useful, it is essential. We must know them. Okay, next slide. Yeah. So what we did, organic synthetic chemist, what he does, he makes all new compound. So like that we prepared a new chemical, okay. And then what we did, we took this thing and then started adding this chloride, bromide, iodide, all these kinds of things. So it did not respond. Whereas the moment you add a fluoride ion, that is the sodium fluoride, you can see that a new absorption speed coming up. You can see that. Okay? You can see it visibly, naked eye, you can see it. The moment you put it in a vial and then add that sodium fluoride ion, you can see the color change in this. And then what we did, we looked into the fluorescence of this also. The moment you add a fluorescence, this peak got enhanced, you can see that. Whereas other anions, it didn't work. That means this is very specific. This chemical what we prepared is very specific to sensing the fluoride ion. Then what we did, other things as you do it regularly with your pharmaceutical analysis, validation of the technique and determining the, limit of quantification, limit of, detection, all kinds of things, which also we did it. And then, next slide. And then what we did is, after that, anion and then cation. So what kind of a cation? Mercury. Mercury is known to be dangerous. You know it very well. If it reaches your central nervous system, the person will become, problem with the nervous system, and he will be behaving totally different. So we have to be careful. So how do you detect that? Making use of the same chemical, we were able to detect mercury very specifically, and then all these cations did not respond to that. That is most important. So how you come up this thing? You had to read the literature. Go back to back slide, madam. Yeah. This chemical which we have prepared needs reading of literature, what other people have published. Okay? Based on that structure, you come up with a new idea. You come up with a new thinking. Okay? And then new design you create. The design is this chemical. So when you use that design and that knowledge after reading the literature or about all the journals and other things, then you decide this molecule might have some significance. That's how it has to go. Once you make it, then you can see the fluoride ion sensing, and sometimes, you know, even if you dream and then plan, read and everything, it doesn't work. It's okay, you have to try again another one. That's how it has to go research. Because you're all M-Pharmacy student, you have to do this thing. Next slide. Yeah. Mercury, there is a clean absorption, increasing the absorption, whereas all these cations which we have used and represented here on this slide do not work. And then mercury, there is a huge change in the luminescence also. Okay? So you can easily sense using our chemical what we prepared, the fluoride ion and the mercury ion very efficiently, which are most important. You can see it clearly, visibly also, which we have published. Next slide. Okay. Now, what is responsible for this color? Again, we have to look into the structure. See, we have prepared a chemical with some structure and then we add fluoride ion. Then what is happening to that? Okay. You can see it here. The moment we add a fluoride ion, okay, it shows a green fluorescence, no doubt. What is happening here? This bond is gone, isn't it? Right? So this lactone ring is being lost. So that's why it shows like this. Green. Which we have noticed in the fluorescence, I told you earlier slide, where if you open up the lactone ring, so that concept is embedded in this design of the molecule. So you require to, develop taste like that, research. How you, lace your research innings, in this way you have to do it. And then again, when you put the mercury, what is happening? You have a sulfur here, and then nitrogen, all kinds of things here. Mercury is known to pull out this sulfur. It has a high affinity towards sulfur. Okay? So when you add mercury, that is pulling out the sulfur and giving you this kind of an oxidizole unit, which is responsible for emitting the red light. Okay? Still you have this lactone ring. Okay? Once you put it with mercury, it emits red light. And then you add fluoride, it becomes green also, green and red. Both emissions are possible. That means the molecule which senses, first part senses and gives you red color, other part senses you and gives you green color. I still have time. So it gives you green color. So different parts of the molecule gives you different color. So this is also a design. So it requires, what we have to do is, we have to read a little bit more carefully and then, plan, design. You will get it definitely. Next slide. This is again chromium ion sensing, iron ion, sensing. That's what we need. The chromium and iron, they are trivalent cations. 3+. Okay. So these are also very important. Iron is very important. Chromium, again pollution. The leather industry people, they use chromium left and right and leaving it to the environment. So someone has to go there, take that and detect it and tell them, no, you cannot leave it like that. You have to store it in a different way. That's what we have to advise. So this is one. There is a change in the absorption and then fluorescence. You can see it by adding the fluorine. Whereas it doesn't respond to all these. Here again we change the design of the molecule. Okay. Design of the molecule actually. Next slide. Yeah, these are the fluorescence curves which we depend. So generating this data is also requires skill in the student's hand. Not all can do it. Generating this kind of a data, you require real skill. Students and all. Okay? You need that skill developed. Because you are dealing with nanomole and picomole quantity. So you have to be extremely careful in doing these experiments. Next slide. Yeah. What we did further is we employed NMR to find out added ion where it complexes. Okay? So here this site is the complexation site. Why this site of the complexation? Where those protons are getting affected, the surrounding protons are getting affected. Therefore, this is the site of complexation. So when you add the cation, it goes and binds at this space. And then that will change the NMR signals, proton NMR signals. You can see it here. You can see. Okay? Very clear. So based on that, you can, when you excite this part of the molecule, which shows emission at 532 using 400 nanometer light. Okay? This is not complex. Okay? When it complexes with the cation, and then when you do 400 nanometer light, this will transfer energy to this and gives you red color. That means energy is flowing from this molecule end to another end of the molecule. This is called fluorescence resonance energy transfer. The moment you add a cation, these two ends started talking each other. A communication link is being established, okay, between the two sides of the molecule just by complexation. This is another important observation which you make. Curiosity. You know, the research should be curiosity driven always. So you call it a fluorescence resonance energy transfer. So it can sense, all these trivalent cation, AlCl3, chromium and 3. It is sensitive to this, not to all kinds of things. That is also we have an advantage. Next slide. Fingerprinting. So you can make use of the fluorescence in the fingerprinting. So we have a couple of publications here also. So, you have a powder dusting and magnetic powder dusting and then spraying method which you use it. Next slide. This is the chemical which we prepared for organic light emitting diode. We thought we can use it because I got a student, forensic science student, 2 students I got it, both are working on that now. Okay. One of them is also working on sensing the ions, which is also important. Suppose if you take something in that you died because of something else, so they have to analyze post-mortem. From that they have to find out the ions also. For that he is doing that. So this is the molecule which we have synthesized. This is also yellow color, commercial, and this is also yellow color. Okay. So next slide. Yeah, this is how we develop the you just take the fingerprint and then dust it on it, and then put it into you might have used TLC chamber. You might have it, isn't it? You just put your that glass piece or surface. You can expose it to the 254 or 365 nanometer radiation. You get all these things, and then you take a photograph using your cell phone. Nowadays we have cell phone. You get this clarity. Then what we determine here is you can use 254 also. You can use 365. 365 is safer compared to 254. 254 is hazardous. So use 365, no problem. And then the concentration level 6, 8, 10. At 10% you can do this, get a very clear picture. Okay. And then further what you can do is you do have this fluorescence microscopy. Okay. You can put this under fluorescence microscopy and get the tertiary level of detection also in your fingerprint. That is most important. Tertiary level fingerprint gives you it gives your fingers, that sweat glands. You can identify the sweat gland and distribution of sweat glands in this, fingerprint you collected. That means primary, secondary and tertiary level also you can do it, so that you can easily detect it. And then, your fingerprints are very, very specific to individual. So definitely you can catch the person with this primary, secondary and tertiary data using fluorescence microscopy. That is what I would like to do. That means fluorescence technique you can use it. Next one. Yeah. Again, you know it about demonetization of our government. So what they have started doing, you have these currency notes embedded with the fluorescence markers inside your currency note. Okay. Anyone can make it, but specific luminescence techniques can be employed here to say that this is the fake note or counterfeit. So there you can use it, the luminescence technology, which is very, very powerful. That's what is being used. You can detect a fake note or counterfeit. So embedding fluorescent fibers into the paper or printing ultraviolet ink onto the paper creates a form of optical verification, easily used at counters, checkouts, and it should be easily used. So that cashier at the counter, he will put your note and then switch it on. It is nothing but your TLC chamber kind of thing only. It has that small bulb or tube light which is having long wavelength and then short wavelength. When you switch it on that, it gives you that light and then it shows fluorescence. Then you say, oh, this is a fake or counterfeit, this is not a good note and this is the original note. You will tell immediately. So it should be easily adaptable. Nowadays those kind of things are available with many people because it's very, very cheap, affordable. That is also important. Checkouts. By exposing the note to ultraviolet light, the ink or fibers fluoresce, revealing the colored pattern not visible under natural light. That is what. You can see this is embedded. These kind of structures which will be missing in that, fake note or counterfeit. So then easily you can recognize and tell. So these are the kind of boxes which you can get it immediately. The chemicals, invariably have to show the fluorescence. That is the remaining text. Yeah. You can detect the diamond also. Okay. How you detect the diamond? Diamonds which have lower fluorescence under UV light appear clear and bright and are considered good. Okay. So if you have a standard diamond, you take it and you think that it is the pure diamond. You keep it with you and compare with all the other diamonds which coming into the market. Okay. You can clearly tell, okay, this diamond is good and this is not that good. So you can verify. Because diamonds are very expensive and costly. And then you need a method, non-destructive method. Here you are not destructing anything. You are getting back your chemical or the item or the material what you are using it. So there the fluorescence makes a big dent there. Because it is an expensive, isn't it, diamond. So you can easily direct a fake diamond or a good diamond or a bad diamond. Next slide. Yeah. This is what I was talking about here. Forensic investigations further. So when a crime is being committed and then a dead body or some blood smears are all, gone from here. When you pull the body, invariably you will have this blood from this part to that part, and then if it is, on the sofa also you can have it, and here, when you wash it with the sink, you do have it here, or in the kitchen, in the sink, all these things. How do you detect that? It is important. What they do in that, Sony TV CID, they spray some chemical. That chemical is nothing but luminol, okay, which we have prepared. So when you spray that and switch off the lights and put something, you get a bluish fluorescence. The technique is being used is the bluish fluorescence. So fluorescence technique is very sensitive to even picogram level. That means even if you wash all these, small trace will be there which you can detect it and say that this is the crime scene. You can easily conclude it authoritatively as a crime scene. That is what. Detect the trace amounts of blood in crime scenes and as it reacts to iron found in hemoglobin. When trace amounts of blood which cannot be seen by eyes blow up with luminol. Okay? That is what it is given. That's what they do it in that. Next slide. Yeah. This is about the luminol. How you make it. Very nitrothalic acid. You condense it with the hydrazine. You get this heterocycle. Okay. And then you reduce the nitro group to NH2, it becomes luminol. So here is the procedure. 10 milligrams of luminol in DMSO in 25 ml of conglomerates, 5 drops of sodium hydroxide. You can adopt it procedure. Even if you can Google it also. If you write Google luminol chemiluminescence, you get all this data. And then you can see the process. This is what the chemical which we use. Which, the problems what we have, India is still buying all those chemicals from outside the country. So you can make all these small chemicals, produce them here and test them and give it to our forensic department or National Investigative Agency, NIA, all kinds of things we can do it. That is what I am asking my students to do that. So it is a service to nation. If we can make a chemical having this application, crime is increased like anything in India, no doubt about it. So these are the small things which we can do ourselves instead of buying it from Europe or Japan or USA. We can stop that. That is the another strong intention what we have in initiating this research. Next slide. Yeah. When you go to the doctor, ophthalmologist, the moment you go, they know that guy will come, some attender or person will come, some small boy will come, and then he says he will open up your eye and put a drop and then ask you to sit for 15 minutes or 5 minutes. Then when you go to the doctor, he will put his torch and see what is happening with your eye. Okay? What is the chemical use? This fluorescent molecule which I have shown you earlier. Okay? So you use that fluorescent molecule, put an eye drop, okay? And then test it after 5 minutes. If your eyeball has some aberrations, when some small foreign material falls into your eye, what you do? You rub it like anything like this. During the rubbing process, what happens? The surface of your eyeball will get damaged. Aberrations or abrasion because of the abrasive kind of thing. So you do have a small tissue of your eyeball is being removed and then there is a small injury occurred to your eyeball. It can be recoverable injury, no doubt about it. So when you put this chemical, okay, into your eye, it sits in that injury. When you shine light on that, it glows. It shows fluorescence. That means you have identified the injury place, specified place where your eyeball got injured. Okay. You can make it. This is a very simple technique which everyone undergoes. Even at the age of 60 or even at the age of 45 also, when you have a problem with your eyes, doctor will do this first test. So he is using this chemical and the fluorescence technique. That is what I wanted to say. Okay. Next. Yeah. This is again, this is most important. You know, when you have a heart problem, how do you detect the blocking of the heart or arteries which are taken up peritoneally or through this, you know, injection? It goes into that. Along with that, what he does, he sends a fiber optic and then that carries the light. Okay? And then when you shine light on it, when you have a blocking at this stage, the artery which is taking blood to the heart, okay, here it is shown. And then they are exposed to X-ray machine. So your chest is being exposed to X-ray machine after injecting this chemical. The chemical goes into the heart and then arteries. Wherever the blocks are there, it will get stuck there. Small amount will remain. Okay. When you expose the X-rays, it shows luminescence. That will determine the site of blocking of your artery, which is most important. Because you have to identify, that is the primary thing, identify. Then only doctor can insert the stent or doctor can use some kind of a medicines which will remove that blocks. Okay. So this is most important. Without that, doctor will not treat you anything. He needs this primary. Okay. Then only he will specify what is to be done. First angiogram will be done. So angiogram is the most important. That technique is based on luminescence. That is what I want to tell. So these techniques, have a lot of biological applications. Next. Yeah, this is the detailed way of, coronary angiography, blah, blah, all kinds of things are given here. Some kind of a biochemistry is also given. Next slide. Vision cascade. See, vision is also important for us. So when you take the rhodopsin, which is in your eye, when you shine light on it, of course, the light we are regularly seeing it. This rhodopsin undergoes all these changes and then goes back to again rhodopsin, right? All these changes were, recorded using luminescence technique. If you look at into the literature and read all those papers, people who have published the papers, they are using luminescence technique to identify all these intermediates in this vision cycle. So the powerful technique, once again, non-invasive, non-destructive, powerful technique is the luminescence. That's what I would like to say. Next, flow cytometry. Flow cytometry, what is this? Very simple. A patient is there, blood cancer patient. Then you must know the cell count. How many cancer cells present and how many normal blood cells present in your blood. That is most important. Based on that only, doctor will decide it is first stage or second stage or third stage, all kinds of things. But you need a technique to determine how many number of cancer cells present and how many number of normal blood cells. Flow cytometry is a powerful technique based on luminescence, which you can apply it for that. This is an instrument available in diagnostics. Many diagnostics you have it even in this V.Jayathirtha also. When you go to the, they will use this flow cytometry to determine the number of them. What is that involved? So what you do is you take this bloods and then process that blood sample and then put it through this. It is a nozzle. Okay, this small nozzle will allow you to put drops and drops where you have probably 1 or 2 cells at a time. Okay, and then before sending it through that, you mix a luminescent marker to that blood. Okay, where that has specifically binds with cancer cells, not with the normal blood cells. Okay, this is the requirement. So whatever you add your luminescent material, fluorescence material, which binds to the cancer blood cell and not to the normal cell. Okay, that chemical should be invented. When you mix that and push it through this, and then you have a laser here. When you shine laser to that, If it is a luminescent, then you will record that luminescence. If it is a normal cell, it doesn't show any luminescence because that thing is not. Thereby you can count it. And an entire process can be done within half an hour. That is another advantage. You require this kind of a test also. Diagnostic tools, diagnostic tests, which are all important. Where the pharmacy candidate is most involved in this, not the other people. Okay? Not even the doctor. Pharmacy students will be, it is their duty to develop all these kinds of diagnostic kits. So here it is being used, and its importance, now you know it. What is the technique? Is the luminescence technique which you use it. That's how I want to say. Next slide. Yeah. So this is the green fluorescent protein where these people got Nobel Prize. Okay. CN. So it looks like it's a jellyfish. It is a purely what we call it academic interest. And the structure of this, it looks like this. For that they got the Nobel Prize. They unravel the structure of this protein, green fluorescent protein. Okay, so they got the Nobel Prize. These three people worked together. I mean, not together, separately, in different countries. But the contribution is towards this. That is what. Next slide. So, what is the chemical transformation it undergoes? This is the amino acid in that, and then it undergoes like that. It forms a heterocycle, which is responsible for the green fluorescence. I always tell you have to find out the structure which is responsible for the luminescence. That is also important. So that is also they found out. That's why they got the Nobel Prize. And these are all the few experiments they do it. Next slide. So what we did also, see, suppose you prepared a chemical something like this, and you want to know whether it is anti-cancer activity it has or not. So to be anti-cancer activity, to exert anti-cancer activity, it should bind with DNA first. Okay, after binding the DNA, it may exert anti-cancer or it may not exert anti-cancer activity. So this assay to be developed. So what we did, we took the calf thymus DNA, CT DNA, right? And then we prepared a solution and added this chemical. This chemical binds with the DNA. When it binds with the DNA, there is an increase in the luminescence. You can see it. We have published this paper also. So the increase in the luminescence is because of the binding of this molecule with the DNA major group or minor group. Okay, that means you can detect this binding of this small molecule with the DNA. After binding with the DNA, it can exert the anti-cancer activity. That's a different issue. Next step which we have to do. But before to see that, you can say this assay and develop, and the luminescence technique is being used for that. Next slide. Yeah, well, this is the DNA analyzer. If you have a DNA, you take the DNA and then add specific luminescent markers which binds with each, base, and then when you hydrolyze it, sequential hydrolysis will give you those bases, and then you push it through them HPLC, and then you get the light. Based on that, you can determine the sequence of DNA. Entire process can be done within a day without any turnover. We do have a big instrument, small instruments are available. You can put your DNA and then luminescent markers, mix it and do it. Instrument will do it and give you by evening. It will give you the sequence of the DNA. So powerful technique of luminescence is being used. Behind this, there is a lot of research going on. That research helps them to define and develop this kind of instrument. Next slide. This is about organic light emitting diodes, which I already told you, which you can make the flexible electronics. Here the electrochemiluminescence is involved. Okay, probably you may get a bag, a vanity bag which you carry will have this kind of a flexible electronics, and then you can change the photos time to time. You can go further. That will be maybe coming up in that. And then all the screens, big screens will be coming up. And then you do have the organic light emitting diodes in a home lighting also. Because it is less, it uses hardly 20 volts, which is nothing. And your cell phone screen is nothing but OLED only. The screen, backside of the screen, chemicals coated backside of your cell phone screen is nothing but this organic light emitting, materials. So this is also electrochemiluminescence is the phenomenon which you observe. Next slide. These are the few, I think I should. Next slide. I think I should. go quickly. So 1 o'clock. Yeah, this is a, is organic light emitting diodes involved engineering, physics, chemistry, and to an extent biology people also will be involved in it. Next. Just skip it. I have put a lot of slides on this. Yes, we can skip it. Yeah, these are the structures which we do it. Next slide. Go further. Go further. Yeah, this is some special fluorescence technique which I have added for you to go ahead. Ultra-fast spectroscopy, which we have a femtosecond laser and then picosecond laser, all these things which we use it to understand the dynamics. That is the next higher level of looking into the luminescence. Next slide. Yeah, these are the dynamics, transition state, electrodynamics, solvent relaxation, all these things we can, process, ultra-fast processors. Next slide. Ultra-fast spectroscopy. Next slide. Amplification and all. These are all techniques This we have it in our IICT, this board and other femtosecond laser. That's why I am showing it to you. Next slide. Fluorescence microscopy, which we use it, I was telling you, which you will also be using it as a pharmacy student. You will be using it. Particularly, we just recently, just 2 days back only, we analyzed our fingerprints using our chemical and took to the fluorescence microscopy, where you can clearly identify sweat glands looking at dots. That is the tertiary structure. So arrangement of those tertiary, structure, that is sweat glands, is typical for each person. So you can identify that person with this tertiary structure also using fluorescence microscope. Next slide. Epifluorescence. There are so many things coming up into the market and other things. Next slide. Confocal microscopy is also next one. Yeah. This is my group. Earlier we have a lot of students. This guy is working for Lotus and he is in Sharjah. He is in Taiwan, and then he settled in USA. He is working as an assistant professor in university here in Guntur nearby, Vignan University, and he is working for a industry. He is working for industry as a manager. And very interestingly, this guy, he owns an industry now as an entrepreneur. One of my students. That is great. He is giving salaries for about 70 people so far now. I hope he will grow further. I am also going to work him after retirement, honestly. He is working for GVK. He is settled in USA. He is assistant professor at NIT Kurukshetra. He is working for Lotus. He is at University, Usmania University, looking for a job, and he is a technical assistant, technical officer working in our division. So next slide. These are some more students which are taken on the next slide. This is the latest group. He is my PhD teacher, Ramamurthy, and he is Uma Shankar, and then he is Lakshmi Reddy, he is Ramesh, he is Jagadishwar, he is pharmacy student, Nagaraju, Pitani Nagaraju, and then he is Mantana Nilatri Raju, and then he is Bharat, and then he is Harsha, forensic science student, and then he is Sasi Kumar. He is now technical officer at ISR Tirupati, and she is a postdoc, and she is also a postdoc, and she is a forensic science student, PT, and then he is Manohar Reddy. He is Appal Naidu, who is coming from this part of Vijayanagar, and his brother is also there in the audience. I know Ganapati, Ejiro the Ganapati, who met me, and he is another postdoc who left to Korea now. This is the group, and I have PhD student, and he is my guy. I thank the director of IICT, Dr. S. Chandrasekhar, all my students and associates. The next slide. Thank you for your kind patience.